We now know why the current in a series LRC circuit reaches its maximum value at the resonant frequency. Here is a graph of current as a function of frequency for the circuit as shown. This curve is often called a response curve or a resonance curve. As expected, the curve has a peak at the resonant frequency of 1000 radians per second. You can see that because if you plug in these given values here, we've got the value 500 ohms for the resistor, 2 henries for the inductor, 0.5 microfarads for the capacitor. So if you use the fact that the resonant frequency is square root of 1 over LC, just plug those values in, you get 1000 radians per second. So there's a peak there. The peak is there because it's at the point where these two are equal, Z becomes just R. The figure also shows graphs of I as functions of W for R equals 200, which is that one, R equals 500 and R equals 2000. The smaller R is, i.e. the less impedance to current flow, the taller the sharper the peak is and the more rapidly it drops off as the frequency W of the source moves away. Looking back at the expression for the impedance Z of the circuit, so looking back at this expression here, we can see the reason for this behaviour. When omega is far away, when the frequency is far away here, when it's in these two regions here, then the impedance Z is dominated by one of the reactance terms. WL becomes large at high frequencies, so the inductance becomes very large at high frequencies, so you get this tailing off here for the inductance. At low frequencies we've got the capacitance is 1 over WC, so low frequencies we're down here. This behaviour does not change when we change R, nor does the value of W0 change, but at resonance, where the two reactances cancel, the height of the peak is determined by R, and the behaviour near resonance is also dominated by this value. Thus a small r gives a sharply peaked response curve, and a larger r gives a broad flat curve, which is down here. You can see these larger values are given a broader curve here. This distinction is crucially important in the design of radio and television receiving circuits. The sharply peaked curve is what makes it possible to discriminate between two stations broadcasting on adjacent frequency bands, but if the peak is too sharp, some of the information in the received signal is lost. Finally, note that the shape of the resonance curve is related to the overdamped and underdamped oscillations studied previously. Reviewing that, we see that the sharply peaked resonant curve corresponds to a small value of R, and a lightly damped oscillating system, a broad flat curve, goes with a large value of R. Resonance phenomena occur in all areas of physics. Other important examples of resonance occur in acoustics and atomic and nuclear physics and the study of fundamental particles, so it's not just for electronic circuits.